Right, another really great way to kind of get comfortable with this is to work problems that are like, okay, if this is rolling without slipping, and all of these are going to be rolling without slipping, we might say something like, if it is rotating at omega, 5 rads per second, then what is the velocity of this point? Okay. Now, remember what we talked about is that at any point, if it's not slipping, that whatever distance from the not slippy point to the point that we care about, and then we go like this. There's always a right angle there. So that point is going down and toward the ground. So if we want to know how fast is this point P going, so if I say, what is velocity of P? Well, first of all, I need to know kind of where P is. So let's pretend that I have a radius of 12 meters, and maybe it gives me this angle is 110 degrees. Okay, so let's see, what can I do with this? So I'm going to take this triangle and just put it off to the side real quick, because what I need to know is length of purple thing, this purple thing. Okay, and because I'm kind of awesome at triangles, I know that, well, these are both radii, so those both have to be 12. And if this is 110 degrees, then I know since these two are both 12, these two both have to have the same angle. So it's 180 minus 110 is 70. So the two of them together have to be 70. So each one of these is 35 degrees. Like, why does this help me? I don't know. It just makes me feel better. Okay. Because I have a 110, and I have a 12, and I have a 12, and I have a 35, and I have a 35. And I feel like at this point there should be something in math that would tell me what the length of that other side is. And yes, you can go in and you can put in this, and then you could do this, and then double it, but I'm going to remind you that you know something called the law of sines and cosines. So the law of sines is the one that's easy to remember, because it's like sine of A over the opposite side is equal to the sine of B over to the opposite side, equals the sine of C, capital C, over its opposite side. So if you have any kind of triangle, the idea is if this is A, the side is A. If this angle is B, this side is B. If angle is C, this side is C, little c. But that should be something you know. So now we actually do have everything. So if I call this R, 110 is to R. It's kind of like a SAT question. 110 is to R as 35 is to 12. So you don't even have to remember the law of cosines if you do it that way. It's just a little bit less steps. So sine 35 times R is 12 sine 110. So R is equal to 12 sine 110 divided by sine 35. Okay, so I can do that, but I'm in radians. Of course I'm in radians, so I need to switch over to degrees. What in the world? I'm apparently changing the sizes of things on my, I don't even know how I'm doing that, but let's go back to, oh my gosh, I can't even see it at home. Okay, so teeny weeny 12 times teeny weeny, oh, which one is sine? I think it's that one. Sine of 110 degrees divided by teeny weeny sine of 35 degrees. And that gives me a radius of 1.2, which seems really small, or a distance of 1.2. Oh yeah, that seems like super bad. What have I done wrong? That's super silly. Oh my gosh, I'm still in radians. It's like completely losing my mind. It's like I just all of a sudden forgot how to do this entirely. I'm still in radians because I looked at the question. I was like, that doesn't make sense. Okay, now let's try this again. 19.7. Holy heck, that makes a lot more sense. Okay, so not that. 19.7. Okay, so if I look at that, does that seem like 19.7? Yeah, it seems a lot more like 19.7 than it did 1.2. All right, so what was this question again? So you always know you're doing good when you've already forgotten what the problem was asking. Okay, so we have this, and what is the velocity of the slippy part? So I already forgot what this number was, 19.7. So this distance is 19.7. And now this has gone from being a super complicated question to a super duper easy one, maybe. In that now I can say, well, the velocity of point P is just omega times r. And omega is 5 and r is 19.7. Remember, this is radians per second, and this is in meters, so we end up with meters per second, so it's a velocity just like we like. So I've got 5 times 19.7. Before I round off, I'll go ahead and multiply, so I have 98.3 meters per second, and that gives me the distance. So, and again, if I give you how fast it's moving, you should be able to work backwards. But really the big key that we're trying to get out of working problems like this is the idea that if I have a point here, well, if it's, if I'm rolling without slipping, then if I ask you for the velocity at any point, the first thing you need to do in your brain is draw this line and then that's the direction of the velocity. I don't know where that other line came from, but that's the direction from the velocity. It's always to the, if I'm rolling that way. If I'm rolling that way, I have the distance to the point, r, times omega r. The only thing is this line has to go to the point of instantaneous, the word I can't spell, center, basically the part that it's rolling on. And then this has to be here, a right angle. And that gives you the direction, and that helps make sure you have the right r. So whenever we say r, it's not r of the circle, it's r of whatever it's rotating around. So again, it made sense that, if I have a circle that's circling on its center, well, this is the instantaneous center. So everything is going, exactly at a right angle here, around and around. And this is quote unquote r. So this is like r of the rotation, right? Because it's the r of how far, what are you rotating around? I'm rotating around this thing back there. What is that distance? So if you don't like seeing omega r and you want to call it omega times the perpendicular distance, omega times perpendicular distance, you can go ahead and do that. Just the idea is to, kind of work through the geometry and just kind of getting a really good solid foundation on this. So whenever you get into dynamics, there's less crazy going on.